So good morning, I am Krishna Kumar from Krishna's class. We continue with our discussion on the primary decomposition theorem. But we look at the special case of that, where we assume the minimal polynomial of t splits into linear factors over f. So we assume that is p lambda is the minimal polynomial is of the form where of course lambda I different from lambda j and our I is different from j. See, these are the zeros of the characteristic polynomial of the lambda i's. These are the distinct zeros that you have. And you know that the p lambda actually appears in this particular form. And this is a special case that we plan to look at. What happens in this case? Now we define, so we have a look at this, but we will just recall for the sake of completeness. So we define Wi to be the null space of t minus lambda I to the power r. Then of course one can show that b equal to this is the part of the primary decomposition theorem. This is the direct sum of W1, W2, etc. W2. And we have projection operators Pi defined from V to Wi such that Pi square equal to Pi, and we also have Pi 0 whenever I is different from. Therefore, the identity operator breaks down as the sum of these projection operators. So this is the application of say the primary decomposition theorem. Now what we want to exploit the fact that the primary, or what is called the minimal polynomial, is splits into linear factors over f. So what we observe is that this lambda 1, lambda 2, etc., lambda k appear as eigenvalues of this. Therefore we write b define d as you recall in the diagonal case we had the transformation becoming a linear combination of these projections with coefficients lambda I. It's the same thing that we are trying to do. Now you see that we are trying. See, the problem when you have Ri, you see, the T is diagonalizable if and only if every Ri is equal to 1. So here we are not assuming that. And therefore it is not diagonalizable. Then what is that you are doing? You are trying to filter out a diagonal part from the given operator. So that we write out in this particular form. Okay, right? So then of course D belongs to clear. They are the sum of pi's, or the scalar multiples of or linear combinations of pi's which are in LG. And also you have the diagonalization. Okay. In fact, the property that you have is this. See, D of Pi V you know, Pi these are elements in W. Sorry, in Wi. So Pi is. So you see, this is that means for D, Wi is the eigenspace belonging to lambda. So that's the operator. So we define an operator for which every vector in Wi is an eigenvector for D belonging to the eigenvalue lambda. So such an operator. So what we do is just remove it from it. So define. So you also observe that T turns out to be, this is a part of the now this is the part of the primary decomposition theorem. In fact, the generalization of a similar statement. This is a special case that appears if T that turns out to be that. Now this, of course, you can write as T1 Tk where Ti and Ti's are, see what you have is that Twi is contained in Wi, that is Wi's are left invariant by T. Therefore, you define Ti in this form and this is what it is. Okay, now let us take the difference of T and D. So T minus D, this is equal to T minus lambda 1 I so define then what we prove is that there is some power of n for which, say r, for which n to the power r equal to 0. So this can be proved by induction. Now you see that n is given by T minus lambda 1 I. Therefore, one easily computes n square. N square turns out to be now we have used the fact that pk square or pi square equal to pi and pi pj, okay, is equal to 0 whenever I is different from j. Also, we have from our construction we know that pi's are polynomials in T. Therefore, it computes with t or even t minus 1. Okay. So we have this result. We have used all these facts. Now one can compute this. You can actually prove by for any r positive integer r n to the power r equal to e minus lambda 1 I to the power r e1 t minus lambda ki to the power r. Okay. This is proved by induction. Now, assume R is greater than or equal to Ri we choose R greater than or equal to Ri. Then it follows that n to the power r, why it is so? So you are taking r greater than r1 say here. Okay. Now you see that what is the characteristic polynomial of this part? I mean on W1. On W1, the characteristic polynomial of t minus r1 I, sorry, t minus lambda 1 I is actually lambda to the power okay. Therefore, you see that this becomes 0 to the power equal to 0 for each, and this happens for each one of these equations. Because you see that the minimum polynomial Ti is I to the power, so you make use of that. Therefore, you have Pi T to the power Ri equal to 0. So that means if you are restricting in Wi, then this is equal to 0. So you get P minus lambda 1 I R1. Lambda 1 I R1 is equal to 0 on W. That's the argument. Okay. Okay. So we conclude that n to the power r equal to 0. So this is the conclusion. Now that means n has the property that from some stage onwards n to the power r becomes 0. So we give a name to this, and this is also one of the important operator. N belonging to LB is nilpotent there exists some positive So what we get is that T is now written as the sum of a diagonal operator and an nilpotent. So this is the breakup that you get, special breakup that you get. in the case where the minimal polynomial t splits into linear factors over f, and that happens if and only if they are triangular. So let us now see what further results we get. One of the questions that you ask at this stage is this breakup? We get a lot of insight into the structure of T. T is essentially the sum of a diagonal operator, that is important. So what we ask is this: is this decomposition a unique decomposition, or we would have more than one such decompositions possible for a given? So the following theorem tells you that this is essentially unique. So unique is so let's with its minimal polynomial splitting as a product of linear functions. Now you see that many situations this happens, because the moment you use f to be an algebraically closed field, every operator t has this property. So this is a given f, there exists a embedding of it in a algebraically closed field. Like R is not algebraically closed, but C is. Okay. You can embed C in R. So many situations this happens. It's not a freak event that takes place. Therefore, this splitting is very important. So let us see what happens. Want to prove that this decomposition there exists a diagonalizable operator B and a nilpotent operator n such that one, two, three already proved. B commutes with n. The operators D and N are determined. And they are well, we have proved, we have shown that T can be decomposed into D plus N. And we also have shown that D and N commute. The reason is that D is a polynomial in T, N is a polynomial in T, therefore they commute. So first let us take some simple examples. Then move forward. And who is a consequence of the fact that both D and N are polynomials. See, this follows from the following. First of all, you observe that every one of these PIs are polynomials. Okay? Therefore, it immediately follows that. So this follows from primary decomposition. Where we have all the PIs. That's the reason. Therefore, they commute. So, commutativity is. Now we prove that how we do this. suppose what you do the usual process. Suppose D is equal to D plus N and T is also equal to D prime plus N prime, where of course D prime and N prime commute. So we show that D equal to D prime and N equal to we prove that D equal to D prime and okay. So from this relation we have D plus N implies D minus D prime equal to both D are diagonal. D and D prime are diagonal and N prime and N are equal. So D and D prime commute and are diagonals. Hence, one can do what is called a simultaneous diagonalization of that. That means there exists an ordered basis in which both D and D prime are diagonal. This is one of the theorems which we have not proved it, but let me just quote it for the time being. And this is a technical stuff which says that if both D and D prime are commute, then we can diagonalize them because it is the same order. That is what is called simultaneous diagonalization. Now what we prove is that N and N prime commute. Hence, we have n prime minus n to the power r. This, of course, you can apply the binomial theorem. This is a finite expansion. Because they also commute, so it doesn't cause any problem. To the power r, rck n prime to the power r minus j. This is the usual parameters. Now, what you need to do is choose R sufficiently large. For instance, you see both n and n prime are nilpotent, so there exists some r1 and r2 for which n to the power r1 equal to 0, n to the power r2 equal to, sorry, n to the power, r prime, so n prime to the power r prime equal to 0. So now if you choose r greater than say some number, say 2r, then suddenly you see that each one of these terms is 0. Okay. So if you choose sufficiently large, because these both n and n prime are important, so we use this fact. This is possible. Because what we have is that if the dimension of the space n dimensional, for if v dimension of v equal to n, then n to the power n to the power n and n prime to the power n are 0. Therefore, it is sufficient to use in that case. You see that every term that is appearing here is going to, that's very easy. Wait. I think hardly needs any explanation. Therefore, there exists some number r such that n prime minus n to the power r equal to 0. What's the consequence of that? That is n minus n prime is equal to. which implies d minus d prime but d minus d prime which implies the minimal polynomial of d minus d prime is equal to lambda to the power r So we have seen already that a diagonalizable operator cannot have its minimal polynomial having repeated steps. Since a diagonalizable operator has a minimal polynomial as its minimal polynomial a product of distinct linear polynomials. The minimal polynomial of d minus d prime cannot have repeated roots. What does it mean? It has to be lambda. Cannot have repeated roots. It has to be lambda if at all it is there. Okay. Equal to 1 and consequently d has to be 0. That is d equal to d prime and n prime. So that rules the universe. Right? So we have seen that if the minimal polynomial splits into linear factors, then you can have another decomposition of d in the form of dx plus as a sum of a diagonal operator and a numerator, and this is the mean. Therefore, It's a very nice representation here. So every operator of this type that is having minimum polynomial, a product of linear factors, is of the form d plus n, where d is diagonal and n is d. So you can actually pull out a diagonal part from it, and what is left is something infinite, and this is the we shall have a look at some examples. Which give you some insight into the problem. I think a part of this example we have already looked into, but nevertheless we will continue. It's nice to complete the we take B to be equal to our neutral side into our dimension of B is then equal to 3. Then we take an ordered basis B as square, and we define E1 equal to Ex equal to A. One plus 2x squared dx squared equal to, then we see that the matrix representation of T with respect to B is given there. So this is required for our computer. One minus 1. That's your A. Now the minimum polynomial, the characteristic polynomial, so also the minimum polynomial the characteristic polynomial itself, namely, so this doesn't diagonalize, so T does not diagonalize. Therefore, T is not diagonal. It's a typical case for the situation that we got. Now we define W1 which is equal to the span of the polynomial and W2 whole square the span of 1 plus x square. All this we will see. Okay. Analogously, for A, W1 in bracket I have written in R3 corresponding to W1. This is equal to the null space of span of and see, I have not chosen, I could have chosen one of these vectors as the eigenvector for A. I will do that. But I want to show you what is happening. This is a two-dimensional subspace. So I am choosing it as a basis for that. Some basis for that, which is continuing to take. Now let us compute this. Because we will compute for A, then from there we can get back the corresponding thing for W1 and W2. Okay. So we have now A of calculus. This turns out to be, this is the eigenvector corresponding of A belonging to the eigenvalue 1. Now A 1 1 0 turns out to be, this you can calculate, and A of zero. So this corresponds to the basis we have chosen for therefore we write the expression for A with respect to B prime, where B prime is ordered basis 1 1 0 in that case, what we have is this. This, then A becomes the following things. So you have got See, it comes out in blocks. Okay, this block corresponds to P1. This block corresponds to P2. Okay, so that's all. And this is the form in which that is. Now let us work out the form. This I write as what are the eigenvalues? I have 1 and 2. So 1 over here and then 2 here. So this I take as my 2. Then therefore what is your n? N the so I will write it this way. So let me write down n. So n is equal to b prime. One can easily verify that zero. Therefore, n is equal to this. That is n is equal to n square equal to this. See that the entire class of vectors in W2 becomes eigenvectors of the operator P. Okay. So you see that P has what is it? Mhm. Thus here 1 by x and x square turns out to be the basis for W. That's what you. Now we choose this a bit more clever and then see what happens. See, the choice of the basis is not make it more. So let me go. Take a different choice. So let me choose B double prime to be and now you see 102 is an eigenvector of A belonging to the eigenvalue so also one two is an eigenvector of A belonging to eigenvalue you get only one linearly independent vector as eigenvector for the eigenvalue. That's the problem. Otherwise, it would have been diagonalized. Okay. So we choose a vector which is independent of the other two and to match it and lying in W. Okay. So for W2 we choose this as the new basis. For W1 we choose the same basis as before. Okay, now proceeding as before, one can show that the representation for E because given by Then D, with respect to D double prime, you choose as 1, 2, 2. Then you see that N which turns out to be simply this matrix. It's a very simple form. That's the advantage if you choose for W prime the eigenvalue corresponding to the eigenvector 2 or the eigenvalues corresponding to the eigenvector 2. But you see that this is not a zero matrix. So N prime is not I want to make some remark. So some remarks possibly disappointed to what you are trying to do. Now if you take up a matrix A, I think I made this remark last time by talking about uniform operator. And you see that this is the same case that you have to sort of optimally. So if N is a matrix of this kind, A n minus 1, and we have entries here A, B, N, etc. A n minus 1. That means on the diagonal it's all 0. Below the diagonal also everything is 0. But above that there may be entries, some may be 0 or may not be 0. This happens, then what happens? Then you see that see n square, when you take n square, this line will shift to the next line and zeros will start appearing. So for each time multiplying with n, this more and more zeros will start appearing, and eventually at some stage n to the power r equal to 0. So that's it. Okay. I just want to make that remark and stop. Right? So next time you can start. So the point is this: if T has its characteristic polynomial or the minimal polynomial written as the product of linear polynomials, then you can always write it up as the sum of a diagonal operator, diagonalizable operator, and then the Thank you very much. Stop.